Now, you're probably thankful that this is my last talk of the day, but I want to talk a little bit about reproducibility. So we've already heard a number of references to this, and I want to talk about the importance of reproducibility, but I also want to connect it back to the idea of better software practices that we've been talking about all day today. So the usual stuff. This is another slide deck that's primarily been developed by Mike Haru, so blame him for everything that's bad about this. So I'll be presenting this obviously, but Mike's really the main contributor here. So I want to talk about some of the reasons why and some of the challenges that we face in reproducibility, how this is coming up now in publication requirements, some of the particular challenges we face in the computing and high-performance computing side of things with the reproducibility, and how this connects to better software practices, and then a few ideas for things you can do to improve this at a personal level. So, my thinking on this is that reproducibility is fundamental to the scientific process, and it gives credibility to the computational results that we produce. So if you do a numerical experiment and you do it again and the result is different, how much can you trust that, right? And if we can't reproduce these things, this is part of the scientific process for other people to be able to reproduce these things. Well, oftentimes we can't even reproduce our own work, right? So there are a lot of concerns here. And it's getting to the point now where this is becoming recognized in the larger world. This is a paper or an article in the New York Times that was about a psychology team who was trying to reproduce a number of studies that were done in that discipline and finding a lot of challenges in actually reproducing it. So these are not the bad guys, these are the good guys. These are the guys who went and tried to reproduce the science and found that they couldn't. There's a lot of different reasons for that. It could be that the documentation wasn't good enough. It could be that most of these are statistical studies. It could be that the statistics were used improperly, right? That's a very common problem these days. But nevertheless, they tried to replicate 100 social science studies, and they could only do like some small fraction. I remember 20 or something like that, pretty small number, right? Why is this important? Well, when the New York Times highlights a science problem, it's probably of some significance, of course. This is only one of many examples that we hear about. We hear about people having to retract papers because of faulty science, faulty analysis, faulty computation. And importantly, I think, it also feeds the public distrust of science. As most of us here, I think, are scientists in one way or another. If you look at the larger world today, you'll see a lot of distrust of science or ignorance of science and discounting of science. And experiences like these don't help. Okay, so it's kind of in our own interest in how we relate to the rest of the world to do a better job with this. Now, high-performance computing has so far mostly been spared the spotlight, right? There's a few cases where, computational results have been retracted and things like that. But a lot of the work we do is for various reasons beyond the typical lab experimental experience, harder to reproduce. We'll talk a little bit about that. And so we're starting to see more awareness. So I think computational science has kind of matured. We initially, reached a level where we had this understanding of the models and enough computing capability to be able to do some things that were sort of qualitatively in agreement with the experiments. And then our understanding of the models improved and the computing capabilities improved. And now in many disciplines, we can do things that are qualitatively in the right ballpark, right? They're qualitatively correct, right? But the next phase, we're not mature enough yet to really have invested the time and attention on ensuring that those results that look to be of good quality compared to the experimental error bounds are actually reproducible and verified and validated, and we'll talk about some of that. But we're starting to see more recognition of this as an issue and more initiatives to help change it. But let's start with what is reproducibility. So it's a bit of a challenge actually right now. So there's a variety of terminology out there. What's displayed here is a set of terms that's used by the ACM, the Association for Computing Machinery. But other disciplines have other terminology and other definitions, and sometimes they're in conflict with each other right now. So we'll talk here about replicable research. Another discipline may use that term in a different way. They may use it in a way that's equivalent to auditable research, right? So you have to watch out a little bit as this, this is a new thing for a lot of scientists, and as people are getting together, they're recognizing these different terminologies, and people are trying to get together and harmonize, but it may be a while before everybody kind of accepts a standard terminology for these things, right? I remember when I got started, when DOE started worrying about verification and validation a few years ago for computational science, there's a lot of confusion over what those two terms meant, right? And now most everybody who practices in the field understands that pretty well. I think it'll sort itself out here. But there's different ideas of reproducibility, right? We do peer review a lot. So we want to have reviewable research is kind of the first level. Something should be understandable enough that somebody skilled in the field can understand and assess the quality of the results and whether they make sense. But that usually doesn't involve replicating any computations that were done. We can go to the next level and talk about replicable research. So this is a way of actually repeating numerical experiments that somebody has done. In this case, we're specifically saying you're going to take the author's code and the author's computing environment and reproduce what they've done, right? So it's a limited form of reproducibility, because we're not going to say that you have to take some work you did on your laptop and reproduce it on Theta, right? Or some work that you've done on Theta and reproduce it on some weird prototype machine built with FPGAs or something like that. It's not completely open-ended. And then you go up the scale and you get increasing independence. You look at different implementations of the methodology and the tools. You look at different computing resources, and eventually you reach a point where this is really reproducible to the extent that somebody could come in with a separate implementation and get quantitatively and qualitatively equivalent results. So right now we're going to focus on replicable research, because that's kind of the starting point for a lot of this stuff. We'll set the bar low initially and then ratchet up over time. So Mike Haru, when he was editor of ACM Transactions on Mathematical Software, instituted a new review process called replicated computational results. This is in parallel with the traditional peer review for the journal. Nothing changed about the standard peer review, but they added a second type of review, which was for somebody to go in and actually try to, if one of these papers came in and it had a graph or it had a table with some numerical results or something like that, somebody could be asked to go in and replicate that work, right? And so then that produces a separate report that is published as a companion to the paper, and the paper gets a label that it has replicated the results, right? And this is a new process. Mike's been working on this for a couple of years. They've had a number of papers go through this. I'll talk more about it. But this leaves a lot up to the reviewer. You have to pick the RCR reviewer well and thoughtfully. We'll talk a little bit about how he does that, and then trust them to do a reasonable evaluation of the thing, that it really is replicable. I'm sorry, I can't speak. But what you get out of it is this additional confidence in the paper that's been published. And by the way, the RCR referee is acknowledged, and they have a publication out of it too, which is also a useful thing. So how do you do this? Well, the fairly common, like I said, there's a few papers out there that are going through this process. This is a little bit old, so there's probably more now. Excuse excuse me. But basically, the RCR reviewer is not anonymous. They are known to the authors because they need to work together, especially in this phase where you're working out the process. But they get access to the author's software and maybe a guest account on their computer system where the work was done, or they can, and they can try to reproduce it themselves following the author's instructions, or independent, or alternatively, they can observe the authors as they're repeating their own results. That's another way to do it. Okay, so that's kind of the process that they're taking right now. It's obviously a first step, but it is a step, right? There are a lot of situations where this is really challenging, right? If you're working on, if your computations need a supercomputer, it may be hard to get access to such a system. The data that went into that table may be too voluminous to save, or it may be too expensive to reproduce easily, things like that. So this is not always useful, but it's meant to be a start. And this is not to say that, this is not meant to be the only check on the software, right? You should still go through the usual things that you would want to do. You want to carefully document the software development and the process that you used for your numerical experiments to go into the paper. The software itself is still expected to have its own verification and validation process. This is not a V&V exercise. This is a reproduction exercise.
In this case, is the publisher paying for this, or is the person trying to get the researcher responsible for these additional costs?
So as with the typical peer review process today, the RCR reviewer is a volunteer, and this can be a time-consuming thing. So that's one of the reasons why Mike worked very hard to make sure that they have recognition, they have a separate publication that they can claim and things like that. But it's a volunteer process right now. The authors are providing whatever resources, computer access, things like that, out of the goodness of their hearts right now. This is, I think, in practice, probably the only feasible way to do this. There are some journals out there that are asking and providing resources for data deposits to go with data in a paper and things like that. We may start seeing more and more software artifacts also being captured in that way, but that's more, in my experience, a matter of archival. You deposit the software and there's a copy of it out there that somebody can get, rather than actually reproducing the experiment. So reproducing is always going to be more challenging and more expensive. All right, so here's Mike's take on the big picture. The real idea behind this is to improve the quality of the science and the ability of others to rely on it. So we have a peer review process that's long established, and generally that gives us pretty good papers, right? We get good text, but how much do we believe the numbers that we see in these papers, this particular number? So now we're focused on trying to improve the numbers. That's what this is about, right? Typically in computing, we tend to trust results because we see similar results coming out from other sources, right? We don't necessarily right now just instantly believe a given result is trustworthy, right? It could still be wrong. There could be still, even with multiple results getting, multiple authors getting similar results, you could still have some problem way back earlier in the process, but this is a first step along the lines to try to address this, right? And once again, we can work on ratcheting up the quality after we get this right. Another aspect of this that Mike designed rather carefully is he's trying to engage what he calls a dark portion of the R&D community. So the reviewers that he's looking for to do the replication are not necessarily the same kind of people he would look for to do the original peer review of the paper. What he really wants for the RCR side is the kind of person who's really immersed in the software, right? Somebody who's working with the software, any software that's relevant in the domain, has the appropriate expertise, but working with the software day in and day out, and knows what it takes to do these experiments and can understand the issues in trying to reproduce them and can work through them with the authors, right? Because a lot of this is about, it's very easy for you to think about the steps that you did to do an experiment and to write those down. But if you had to hand that list to somebody else and get them to do it, you'd probably find twice as many things that you forgot to mention because they're in your head and you're not even thinking that they're important, okay? But so Mike's trying really hard to engage this other pool of reviewers who are practitioners and users, other software developers and things like that, rather than the really, the high-end people that you often want to get to peer review something for the sake of credibility. And so he's been pretty successful in that. And he's also beginning to get some change in the community. This is an email that he got. So this is a submission that wants to go through this replication process. And they say, to make it easier, we've preserved an exact copy of the code we used for these results, including additional capabilities that are not in the public version of the code, right? Well, that's good science. We would want them to do that anyway, right? But now there's an actual motivation for them to do it, right? Because it feeds into this replication process. So this is Mike's contribution to push this forward. Another thing that you may have seen if you're involved in the supercomputing conference series since I think 16, they've started introducing a reproducibility initiative there. And it's evolving now. It's become a requirement that you participate in this for your papers to be considered for best paper awards or things like that. In most other cases, it's optional. I've seen some of the workshops who are requiring the reproducibility artifacts here. And what they've done with this process for SC is have a couple of different things. One is an artifact description. So this is a separate, it's kind of an appendix to your paper that describes in some detail the process that you went through to do your computational experiments. If you ever read papers in the experimental sciences, they usually have methods or instrumentation and methods set up a section or something like that where they're trying to document all the stuff about the instrumentation they're using and how they did the experiment and things like that. This is kind of the equivalent in a way, a level of detail that we don't usually put in computing papers. Okay, and then the second level, so as it says here for SC19, this artifact description appendix is going to be mandatory, right? So this is just step one. Step two is this artifact evaluation. And this gets towards the trustworthiness or the replication argument, but it recognizes, especially at a conference like supercomputing, a lot of the work that's going to be published here is targeting special boutique systems, high-end systems, really expensive computations, where you can't necessarily go in and reproduce them. Okay, so this is not actual replication, but it's more like describing the process that you went through to ensure that the results you're providing are good. Okay, so you're describing your own checking and evaluation process. And you're exposing that to the community, to the reviewers, and they can say yes or no, and they can give you feedback and things like that. And hopefully, once again, this is something that we can learn over time and ratchet up. Any questions about these things or comments? Has anybody submitted a paper to SC in the last few years who's done these appendices? You have? Yeah. And what was your experience? Were they hard to write? Mm-hmm. Yep. This is, by the way, if you write a proposal to NSF or DOE or just about any other federal sponsor these days, they will ask you for a data management plan, right? And the fundamentals of the data management plan are right now the ability to provide in an unambiguous, machine-readable form the data that you've presented in your paper, right? So the tables or the graph, the data that went into that graph or things like that, be able to put that data out there so that somebody, back in the old days, my wife used to do this when she was in graduate school, somebody would put a graph in a paper and they actually had a program where you put the cursor down, points on the graph, and it would digitize it for you. Right now we just take a picture of it with your phone, but still, that's very error prone. So this is an attempt to get beyond that. The data management plan is an attempt to get beyond that, and this artifact evaluation process is a similar thing for the software and the process that you use to do the work. So these kind of things are catching on. If you're interested in supporting these kinds of activities or maybe avoiding them, you can look at some of these places to find, this guy Fersen has a list of conferences and journals that have reproducibility requirements. This is coming more into other ACM journals, and the ACM has started providing badging that displays that you've been through this artifact review. And you'll be able to select for, I only want to see papers that have been through the RCR process, right? Because they're more trustworthy. But we still have challenges. So we do a lot of big computational experiments that can be hard to reproduce. So you do some kind of hero calculation. What are your options, right? If the reviewer questions your results, well, it's unlikely that the reviewer is going to be able to rerun on their laptop or whatever, even if you provided them all the inputs and code and stuff like that, right? Would the reviewer probably be able to rerun on Mira itself? Maybe if they had an account there. Otherwise, it could be a really long process to get an account, get an allocation. 5 million hours is a fair amount, right? You could rerun your code. But do you have the allocation to do that? Is that how you want to spend your allocation? Okay. Well, maybe if you don't do any of this, your paper gets rejected. Could be. Okay. Or your results are accepted, but there's a risk there. They might not be right. Right? And you might have to retract the paper later. That's kind of embarrassing too. So we have issues here. And it's not just hero calculations. I'll tell you an experience I had writing my PhD dissertation. So back then I was a quantum chemist, and I was implementing some new methods, right? For one of them, I was the second person in the world to ever implement this method, and they had published one paper that had results on one molecule, right? And then I was doing some new stuff beyond that. So I was implementing this thing, and of course I was comparing with this other paper, and my results weren't matching up. So is my implementation right? Is his implementation right? Are we both wrong? We can't both be right. So this really, I spent a long time over this, and like a week before my dissertation was due, I finally realized that I had transposed one matrix, and that was my problem. So it's not always just being able to reproduce a calculation, but being careful about what's in the calculation. So you should think about how you want to make sure that the results you're producing out of your simulations are correct. I did a lot of stuff when I was trying to debug my problem so quantum chemistry has a lot of different symmetries. And so I would flip all the different symmetries and try to take advantage of them everywhere I could. And that's how I eventually tracked it down, right? Because I knew these symmetries should work out, and I knew it should be the same if I flipped the matrix and things like that. And you should think about, in your situations, what you can do, maybe completely artificially, to try to check that your calculations are what you intend them to be, right? So you can create synthetic operators that you know something about. You know the spectrum, you know the rank, or things like that, right? You may be able to do something with invariant subspaces or with properties of the matrices. There may be some conservation principles that you can take advantage of, right? A lot of these things we talk about, in general, we talk about preconditions, postconditions, and invariants. If you have certain conditions going into an algorithm or a routine, there are certain things that routine should guarantee will come out at the end, postconditions. And there are certain things that are inside there that will be unchanged, certain conditions that will be invariant. Right? And you can think about those things, and there are actually some languages where you can specify these things. It's part of the testing, supports the testing process. And so, these are things you may not want to do on a routine basis in every production run, But when you need to test or when you need to debug, having these kind of things built into the code and being able to switch them on and off is really, really useful. So have you guys thought about this at all? What would be some of the things that you might be able to do in your disciplines that would be useful in this way? Guys have any thoughts?
I have a problem with my code, for example, that is, it happens also with another codes that is that you have certain mechanisms that are random. For example, in deep learning you have a technique called dropout that is random, and you how can you test that kind of behavior? Because it is random. You can test it with a benchmark, and
right.
if you disable that ability, the network is not doing what it is supposed to do.
Oftentimes for random types of environments, you can do something with the statistics that will be informative. Like Monte Carlo simulations, you can examine the convergence properties and things like that. Also, in some cases, it might be useful to do a reproducible random number generator, right? So if you can choose specific seeds, and then you can reproduce the stream of random numbers, and that should give you a certain kind of reproducibility going through the reruns of the simulation. You have to be careful about misusing that, but that can be useful for debugging and things like that as well. I need to wrap up, so I'm going to move on to just a little bit of how this connects with software productivity, right? So productivity, which we've been talking about but we really haven't defined, is some measure of the unit of output per the unit of input, right? We don't necessarily have to use a big complex formula for that. We can have a feel for when we're doing better or worse with what we're getting out of a process depending on what we're putting in. And sustainability we think of as the future cost of usability. So being able to carry something forward, what do we pay now versus what would we have to pay over time if we didn't think about sustainability? And the idea is that you can often pay less now and get the payback over time because you've reduced your ongoing costs. Okay? And so I would argue that a lot of the things that we talk about for productivity also impact reproducibility, right? So there's a common statement, better, faster, cheaper, pick two of the three. What we want to try to get to in a productivity sense is being able to do all three, right? So here's a case that is probably familiar. You're behind in developing a new model for your software and you need results for an upcoming paper you have a deadline for. So how could you get around that? You could do a simpler model. You could work on it, set other work aside and work more on this project. It may or may not be possible. You could ask for an extension on the paper deadline. You could do the sophisticated model but don't bother to test it because that takes time, or you don't document it or check it in. Well, none of those are a particularly good solution, but if you invested in developer productivity, you might be 6 months from now in a better position where you're able to do the work faster and better because you've made this investment. And now you're on track in developing that software and you've got the results for the paper and you can meet the deadline. We can take that further and invest in software sustainability. So this is looking over a longer time frame. And once again, you're doing a better job. It takes more time to realize some of these kinds of improvements, but now you're doing more sophisticated models and you're publishing papers about it and you're doing a much longer term view of things, and that can be really useful. And it's not impossible. All it really takes is step-by-step improvements and focusing on your productivity and thinking about how you're doing things. So which of these things do you think enhances reproducibility, to connect software practices back to reproducibility, right? So performance is a common thing that we worry about, but it's also something that tends to go against many quality software quality metrics, and also tends to reduce reproducibility. But a lot of these things, better testing, better source code version control, and investments in productivity and sustainability all feed back into the ability to reproduce results better. And we can turn this into a virtuous cycle if we want to. It can be hard to get people to invest because it's an investment. They don't see an immediate outcome. But if we start looking for ways to provide more recognition for these things, impose quality requirements on the software, impose reproducibility requirements, we can set the demand for some of these practices and help create a virtuous cycle. And then this is a quickie thing that Mike has about personal expectations. So this is a quote from Mike: "Show me the person making the most commits to an undisciplined software project, and I will show you the person who's injecting the most technical debt." Right? It's easy to optimize for stats like how many contributions have you made to a project, but that's not necessarily what you want to optimize for. It's not necessarily the most productive way to proceed. Even though this count of commits is really high, you might be better off spending your time on some other things, right? Doing a better process of designing your software and documenting that software design process, working with some GitHub issues to actually maybe address some of the bugs that are already in the software that might impact your results. You know, there's a lot of other ways of maintaining content and things like that. Mike has a little magnet that he has produced and given to his team, and wants them to look at it every day. And he asks them to think about whether they're really working on improving their productivity, and asking whether their work is traceable. Does it connect up with things that are recognized and documented in the project? Is it recognized as work in progress that you should be doing? Or is it just something that came in that maybe you should defer or get somebody else to do or something like that? Is the work you're doing sustainable? And what can you do to improve your work processes and your contributions? So to summarize, reproducibility is becoming more and more important, and we're getting more and more expectation for reproducibility at some level. It's really challenging for HPC, but it's not impossible. And a really important way to deal with it is to improve your software practices so that you have more time to do this, and a lot of the same practices that improve the code quality will also improve the reproducibility. All right? And here's a couple of other resources from Mike.